to check the second session of the day about image processing. So the first talk is by Irina Voiculescu from University of Oxford. And she's going to talk about internal state cellular automata and their applications to image segmentation.
Thank you very much for the introduction. So we're moving way away from control theory. And I'm going to talk about image segmentation in the computer science sense. So what we do, our main motivation and long-term research interest is segmenting medical images, as in images that come from CT scanners, MRI scanners, anything that the medical community gives us to process. And what we aim to do is to label features into those images and then align the labels and do 3D reconstructions of those tissues. So we want to turn scan data into volumetric measurements. But in doing so, what we end up doing is partitioning the images into regions that belong together, pixels that belong together. And this, of course, can apply not only to medical imaging, but to any imaging. So we could think, I mean, if you're into robotic, then it could be the vision system of a robot. And it can also be frequencies from any other type of source. So it can be radio frequencies that are represented as intensities, as are represented as an image, essentially. So it can be an image of anything. So I won't restrict, and we haven't restricted this paper to medical applications, but rather what we've chosen to do is to take a publicly available data set, such as the Berkeley data set, and do image partitionings onto that data set. So you have here a preview of what we're aiming to do. We're aiming to identify features in a grayscale image. And we've also created our own synthetic data because we wanted to start with, we wanted to know whether it works on very simple examples, but with some noise present. And our original approach, and what we do most of the time, is to use all the other imaging techniques. So we do watersheds, we do learning, we do feature identification through contours, we do all the other things, but we wanted a novel approach to this problem. So what we're using is cellular automata. And if it's too long since your first year computer science, I'd like to remind you what we mean by this, and then I will explain how we generalize this very simple concept to more and more to introduce more and more complex features to it. So first of all, here I'm giving you a one-dimensional example. So I have a one-dimensional array of independent agents, independent cells. These are the cells, the cellular automata. And each cell will change its state according to the state of its neighbors. And the state here can just be 0 or 1. So this is at time 0, the top line of that, and the second line of that is what happens at the next step. Yeah? And here are all the possibilities, 0, 0, 0, 0, 0, 1, etc. So if I am in the middle, I am the agent, I look left and right of me, and based on my neighbor's states, I do something. And this is already a pictorial representation of what I do. It's not unique, obviously, it's a rule that I, as the imaging agent, as the algorithm, can impose. So this is the rule that we've developed for our imaging. And here's an example. So I start from an array which is all ones, apart from this little pixel, which is a 0. That's at time equals 0. Then you can see how that evolves to time equals 1 based on this rule, time equals 1, 2, 3, etc. And we see a pattern emerging from this. And the pattern emerges from the independent behavior of these cells. They independently, simultaneously at each step, develop according to that rule. So here's what we do. This is the classical definition, and that's for binary values. And you can already guess that the next thing to do is to generalize this and to say, okay, I'm still in a one-dimensional space, I'm still an independent cell, I look left and right of me, but now left and right of me I can see any grayscale value. And what I'm trying to do is to work out whether to team up with my left or with my right. So essentially I'm trying to produce teams out of these possible values. And I can produce two teams, so I can aim for the pixels to converge to 0 or to 1, or I can produce several different shades of gray of teams based on these rules. So what we have, and I won't discuss this here, but we have essentially some parameters. So I look, and if my neighbor is close enough, then we decide to be in the same team, and I take my neighbor's value. And if my neighbor is far enough, then I decide that between me and my neighbor, there will be a boundary of my team. And we can then study the interplay of these parameters to work out what happens in such situations. So here you have an example. Again, it's a unidimensional example. I just made it very big so that you can see the shades. And we start with some stripes here, and what happens eventually is that they all tend to converge towards black or white. They won't be completely black or white, so this is after 34 iterations of this process, but we can do something like a thresholding system to work out which ones are mostly black and which ones are mostly white. So that's in one dimension. And of course I can now move to 2 dimensions, so that's a further generalization. So I'm still into a grayscale space here. And instead of just looking left and right, I now have a choice for what a neighbor is. And there are many such choices. Here's 4 of them. So these are von Neumann neighborhood. This is a Moore neighborhood. I can look immediately around myself, or I can extend my my lookout further out. And I have more or less the same options, right? So apart from that, I still need to work out which of my neighbors to team up with and roughly what they will look like. And so I still have what is close enough, what is far away. And we defined a rule in a paper we published earlier this year at EvoStar. We define rules based on how close my neighbors are. So this is me in the middle, and this is not physical distance in the image, it's the distance to the grayscale value of such neighbors. And there are, of course, many other neighbors. Here I've only shown the closest and the furthest. So there's a closest and the furthest, larger than myself, greater than myself, and the closest and the furthest, smaller than myself, and I can decide based on those. You will see the rule in that paper. And you can now guess where this is going. We're finally arriving to intervals. So the problem, or one of the limitations of the scalar approach, is that if I take my neighbor's value and I am its closest neighbor, then my neighbor will take my value. And then this value exchange keeps happening, and it's not really converging very successfully. So what we do instead is we say our team is a range, an interval that is between my value and your value, and let's see if we can co-opt others to come into this range. So instead of keeping a single scalar for this, we now keep an interval, and we have to now reinterpret what does it mean to be in the same team. And for that, we need to look at relative positions of intervals. This is not new. It was defined by Kiryaev in a technical report in the 90s. Many others have looked at that, but this is absolutely key to how we define team membership. And we've tried a few samples, but I think that there is a vast amount of other options, and I think that this is something that will eventually need to be refined for the specific application of image segmentation. So what we've done here is we've said my neighbor is smaller than me if it's in these relationships, which is roughly those up there. Then my neighbor is the same as me if we overlap. So if one is included in the other, or they're identical, and otherwise it's greater. And we can apply something very similar to scalars here. And again, there are interpretations. So here's an example where I've shown how there's overlap here, and as humans we can see that those two belong together, right? That those are clearly in the same team, because look how far away the others are. Okay, now the question is that distance, that epsilon there, is that large enough to warrant a boundary there, or are those pixels still in the same team as these, and there's just a gap, and maybe at the next iteration or several iterations down the line there'll be something else joining that gap. And this is where the interplay between epsilon and delta is going to come in. So what we've done is we've defined a Hausdorff distance between these intervals, and here's a sample rule, right? There are many variations of this rule. I'm illustrating a simple one because it fits on the slide, but as you can see, I'm only changing my value. So again, this is me in the middle, and I'm going to change my value, the value of my team, according to only what the pixels which are closest in value to me do. So I'm simply looking at the distance between those two, and I'm completely ignoring the pixels which are further away. But of course, we can imagine many other rules where we can also take those into account. So there are a lot of variations possible, and there are also variations on the relative positions of the interval. And that's essentially what we do with this. So we apply these rules to the Berkeley dataset and to our synthetic data as well, and we let it converge for about 50-60 steps. After that, it's fairly clear. It progresses very nicely up to that point. And for this particular application, we've chosen to do just two teams because the data set is such that there's a clear single feature in each of the images. For medical applications, it won't be that easy because there'll be more than one feature. If you have an abdominal scan, then there'll be several organs there that you'd be interested in. So there'll be more overlap. And these are our results, and you'll think, well, that's not very good. But what we've done here, which is less than we do with the medical data, is that we have deliberately allowed for this to run on the raw data. So we haven't done any smoothing, we haven't done any other processing, any filtering before, because we wanted to see the contribution of the cellular automata by themselves without the other pre-processing step. What we would do with a medical image is that we would do a Gaussian filter or an anisotropic diffusion filtering or something like that to emphasize the boundaries and to smooth it, and then we would apply whatever other watershed segmentation partitioning method that we do. So that's what we're doing deliberately here. When we get to the next step, we will do that. And we also, in medical imaging, tend to work with the gradient magnitude image. So instead of working with the raw data, we look at the gradients in each direction, and we combine those to see where the steep edges are. And we feed into our watershed algorithm, whatever other segmentation we use, we feed the gradient magnitude image rather than the raw image. And again, that is something that we could do in this case. But we wanted to highlight the contribution of just this particular kind of step of algorithm to the data. And so I've only showed you pictures in 2D because we can interpret them this way. But it's obvious that because these agents are independent and they update themselves simultaneously, in fact, the method is dimensionality independent, right? So I can do it in 3 dimensions, so I can take a whole volume of scans, and that's what the CT scanner gives me, in fact. It gives me a slice after slice after slice, so I can simultaneously update all the voxels in a 3D volume, or I can work with a 15 parameter space. If I get data from the different kinds of sensors, I can just look at all those intensities, and I can cluster the parts of data frequencies that I'm interested in using this exact same method. So although I'm calling it an imaging method, it is something much, much more general. So there's no user intervention. We wanted that very much because one of the main issues we get with the medical data is that the clinicians are simply not interested in sitting there and drawing contours or giving us clicks or giving an opinion. If they want any measurement from what we do, on the whole, they would like the machine to have a go to start with. And that's also a reason why they are not so keen on machine learning, on conventional machine learning algorithms. So we have no training data usually for any machine learning that we do because they're not keen to give us, and this method fits that category of algorithms because it's completely unsupervised. We do some reinforcement learning for our imaging, and I think that there is scope for doing reinforcement learning with this style. There is scope for calling this a search space and doing a reward function, all that, but we haven't. This is some time into the future yet. And essentially what we are illustrating here is that we can obtain a global behavior on our state space based simply on just local rules. So each agent will decide based on its locality whether it's at a boundary or whether it's inside a team. We've been doing this work with colleagues from the university in Cluj, and I'm grateful for the funding that they actually provided for this project. Thank you very much.
Thank you, Irina, for this interesting talk. Any questions, audience?
Yes, thanks for the talk. Is there any issues to generalize to hierarchy functions? I guess images are 2D problems, so I wonder if you could consider objects in an empty space, large space.
I think so. Yes, that's what I was saying. That one of the things is dimensionality independent. So for 3D, it's immediate because in 3D we get the volumes and we have a way of checking it. If we generalize to a multi-dimensional space such as a multi-parameter system, we will need to look at a way of validating the results. So there will be some results coming out, but we will need to look at how to validate that the results are semantically significant. But I think the generalization is immediate, yes.
I was thinking about merging boxes that maybe allow you to operate decision algorithm using transactions, contractions, and but virtual boxes that have strange shapes there. Don't you would like to glue them together in a efficient way? So I wonder if I was wondering whether your approach may be
I would say yes, but let's have a go on the back of an envelope in the coffee break.
Okay.
I have many questions concerning the clustering operations performed by your approach.
So you mean after the iterations, how do we threshold? Yeah, and
so
again,
you determine clusters. I mean, it would be interesting to compare this method with an unsupervised learning algorithm.
yeah.
Well, no, so it's the K-means algorithm. On the other hand, we have seen some efforts, research efforts on the side of neural networks, such as the self-organizing maps of component, which use interval data. So I would propose to discuss a little bit.
With great pleasure. Yes, absolutely.
Yeah.
So I swept under the carpet anything to do with what we do with the results at the end. So I just said that we do histogram-based thresholding. So we draw the histogram and we work out roughly what's 1 and what's 0. But what in practice we would like is, like you say, clustering of the semantically related values there. And we would want more than just 2 values.
Yeah.
So we only did this because it was suitable for this data set, but ultimately to generalize, we would want a clustering.
Other interesting issues also.
Yeah.
The areas around the segmented part of the image, which are uncertain, these are much more interesting than the main core of the cluster.
Mm-hmm.
For some clinicians, the most information on the let's say the uncertain area than the core itself.
Yeah.
Okay, but
we can take it offline.
Okay.
Thank you.
What else? So from what I understand, you haven't done any comparison with like a state-of-the-art segmentation techniques.
So we haven't compared this particular one. So the Berkeley dataset comes with some gold standards, and what we have is a series of metrics. So again, what we would do for validation is to define a metric, and that can be either overlap-based. So we compare this aeroplane with the contour which was drawn by a human, and then we calculate the percentage of overlap. And there are umpteen different metrics, or you can have a distance-based metrics, like the Hausdorff distance. But we have had so many of these. So these experiments, we have tried so many rules of this kind, and none of them were immediately the most appropriate one. So some worked better for some images, and some worked better for other images. So we haven't produced a complete graph of which ones are better, because we are still in the process of refining those. We have them for scalar. So I have an implementation of cellular automata approach to segmentation for scalar methods, and there we are close to the state of the art, and we've also parallelized it on the GPU, and it works wonders. It's milliseconds. But the validation is still ongoing.